It's good to see everyone. We just heard an excellent ITC colloquium by Stella. Ocker, where is she? Stella? Oh, over there, yeah. And we will hear from her again. She told us about the electron density distribution throughout the Milky Way. And she will tell us about, she's from Caltech, and will tell us about probing the low velocity regime of non-radiative shocks with neutron star bow shocks. And after that, we'll hear from Shaunak Modak from Princeton University, over there, who will tell us about characterizing surface density and potential fluctuations in the interstellar medium. So we hear a lot about the interstellar medium today. And then Andreas Burkert is here, all the way from Germany. Andy? Oh, over there, yeah. He is, are you at LMU or currently? You are at LMU.
I am at several.
Yes.
MPE, LMU,
Yes.
and whatever.
Okay, so you are a quantum object.
Yes, exactly. And now I'm here.
And we'll hear from Andy about the puzzle of super thin, ultra cold galactic disks at cosmic dawn. And finally, our own student, Will Golay, over there, who will tell us about the first VLBI-Resolved non-relativistic radio outflow from a mid-infrared tidal disruption event. And that's very exciting. We'll start with Stella.
Can we use the mic again, or not?
Yeah, it's because
Yeah.
it's recorded. We need that.
Okay. So my background is primarily in radio astronomy, but when I started my postdoc, I decided I wanted to learn how to become an optical astronomer, and I decided to do that using a hobby interest of mine, which is neutron star bow shocks. So bow shocks are ubiquitous in the ISM. They are generated by stars moving at supersonic and superalfvénic speeds. And most pulsars, or neutron stars, produce bow shocks because most pulsars move at hundreds of kilometers per second through the ISM. So it turns out that neutron star bow shocks are Balmer-dominated, similar to shocks found in supernova remnants. So typical of Balmer-dominated shocks, they exhibit strong H-alpha emission, which can be separated into broad and narrow line components based on the contributions of both charge exchange and collisional excitation to the H-alpha emission. You can see a nice example of a Balmer-dominated shock in supernova 1006 up here. Now, the kind of classical picture of these bow shock structures is that you have some stellar wind, which is pushing out against the ISM. And so the shape of the shock is determined by the conditions for ram pressure balance between the wind and the ISM gas. So you have some region where the wind is freely outflowing, and then it starts to feel the pressure from the ISM. It becomes shocked, and it eventually reaches pressure balance with the ISM at a region known as the contact discontinuity. And we see H-alpha emission arising from the region between the forward shock and the contact discontinuity. So it turns out that for pulsars that have some spin-down luminosity E dot, which is carrying away the energy of the wind, then your expression for the standoff radius, which is the distance between the contact discontinuity and the star, has this expression. It depends on the spin-down luminosity, the density of the ISM rho, and the velocity of the neutron star relative to the ISM V star. So this is the very simple case of what a bow shock could look like. But in reality, the neutron star bow shocks we observe are often far from this classic shape. So here you can see a rogues gallery of some of the neutron star bow shocks that we observe. These are all narrowband H-alpha images. The nicest looking one, or simplest looking one, is the bow shock around the nearest millisecond pulsar, JO437. But you can see here that in general, these bow shocks have kind of wobbly shapes, undulating morphologies, which are related to a combination of projection effects, density fluctuations in the ISM, and potentially anisotropy in the pulsar wind. In some cases, we have very high resolution HST imaging of these bow shocks. You can see one example of this on the right. This is the so-called Guitar Nebula, which was discovered back in the 90s. And we actually have HST imaging of this bow shock ranging for well over 20 years. And you can see zoom-ins on the head of this bow shock here, and we actually can see the bow shock change over time. That's because this pulsar is moving at about 800 kilometers per second. So over just timescales of years, we can actually see the motion of the pulsar exhibited in the changing bow shock. So bow shock morphologies can constrain both the properties of the neutron star and the ISM. So based on this expression for the standoff radius, this becomes very clear. The spin-down luminosity actually depends on the neutron star moment of inertia. So in principle, you can relate that neutron star moment of inertia to the neutron star mass. So this is actually another way of probing neutron star masses. It's also sensitive to anisotropy in the pulsar wind. Of course, you can also constrain ISM density and the neutron star velocity. All of these parameters are degenerate, so in practice, you need some way of breaking those degeneracies. And one of the ways of doing that is by having a resolved velocity structure for the shock. But the reality is that most studies of neutron star bow shocks to date have relied on narrowband images. We are only seeing the shock in projection, and it is very difficult to disentangle these different quantities of interest. So I undertook integral field spectroscopy of 3 neutron star bow shocks last year with 1.5 nights on KCWI. I'll try to flip through some of these bow shocks. So here you're seeing the emission as a function of observing wavelength or equivalently radial velocity. This is all centered on H alpha. So here's one. Let's see, here's the next one. This one is my favorite because you can actually see that the H alpha emission first appears as these outward moving lobes. And I think this is pretty direct evidence that the wind of this neutron star is predominantly equatorial. So you can see these lobes spread out and then eventually light up the whole shock. And then this pulsar on the right, this is actually the head of the Guitar Nebula. And this one is nice because you can see that the emission really starts to appear sharply at the very head of the shock, which is directly where the neutron star is interacting with the ISM. And then as you go to lower and lower radial velocities, the whole subsequent length of the shock lights up in H alpha. So here's a more succinct overview of those 3 different shocks. Now you can see the H alpha emission as a function of radial velocity. So you can see that we're probing radial velocities that are roughly on the order of a few hundred kilometers per second. And there's a lot that we can do with these data, right? Integral field spectroscopy provides very rich data sets. One of the things that we did was we examined the broad and narrow line emission. So we were actually able to resolve the broad and narrow lines for these 3 shocks all for the first time. Here you can see the prettiest example. This is for this pulsar bow shock J1741. And so on the right, you can see the broad and narrow lines for 3 different regions in the shock. And the key thing that makes these shocks different from bomber-dominated shocks and supernova remnants is that we actually see, because this is a conical shell, we see the broad line split into 2 components with the narrow line at the center. So this velocity structure gives us a lot of information. One of the things we can deduce from it is the inclination angle of the shock, which actually tells us about the radial velocity of the pulsar, which cannot be measured by any other means. So we actually used basically the red shifting and blue shifting of the shock emission to constrain the inclination angles of these shocks. You can see that depicted here. So the intersection between the solid black curve and these 3 horizontal lines, which are the measured ratios of blue to red emission, give us a constraint on the inclination angle. And we'd like to do a much more precise job of actually modeling the 3D structure of the shocks to get tighter bounds on the inclination angle, which we can then use to infer tighter bounds on the pulsar radial velocities. Another thing that we can look at is the ratio of the broad to narrow lines. And one of the things that we find is that in all of these cases, the broad to narrow line ratios are very large despite these shocks' small effective velocities. So here you can see a comparison between the broad to narrow line ratios that we infer from these observations versus effective shock velocity compared to supernova remnant measurements. And so one of the things that we see is that these neutron star bow shocks are probing a very low velocity regime of non-radiative shocks, which are not accessed in supernova remnant observations, because for supernova remnants, the radiative transition velocity is actually higher than the effective shock velocities for these pulsars. So this is really probing a different regime of non-radiative shock physics, which has actually not been explored yet in simulations. Why do we care? Well, the broad to narrow line ratio is an important diagnostic of electron-proton equilibration in these shocks, which has implications for cosmic ray acceleration. And so moving forward, I really hope that some simulators decide to take up this problem and look at how the broad to narrow line ratio behaves in this low velocity regime so that we can actually start to disentangle what these measurements mean for cosmic ray acceleration in neutron star bow shocks. So with that, I will take any quick questions.
Stella, this is beautiful, but one question, the energy comes out of the pulsar in a relativistic form. There's some relativistic wind, which makes the shock quite different in the sense that the piston that is producing the shock is relativistic fluid. So that affects the shock jump conditions. And did you look into that? I mean, perhaps in addition to the shock velocity being different, there is another qualitative difference from supernova, where you have non-relativistic fluid pushing out the ISM.
Yeah. I mean, the short answer is yes, and I think there are maybe some simulations in place already where we can start to look at this. Like people have simulated relativistic pulsar winds, and calculated what the bow shock structure would be. But the short answer is I haven't started to go into that in detail. So TBD.
Okay. Comments, questions? Oh, please.
Thanks, very nice talk. About the diagonality you were saying on the stand of radius. So we're wondering if one could use radio observations and then estimate from there from the slope of the radio, estimate the Mach number, and so come back to the velocity you were mentioning.
Which velocity are you referring to again? Sorry, I didn't catch
So that would be the velocity of motion of the pulsar within Interstellar region, the one which can raise the shock.
Yeah, so I mean, from radio observations, at least in the timing sense, we get from pulsar timing the transverse velocity of the neutron star. But as far as I'm aware, there's really no method for getting the radial velocity other than this method. Now, you can try to do things like if you, for example, have a neutron star that's in orbit with a binary companion, then sometimes the timing can give you some constraint. But yeah, in terms of using the Mach number, I'm not sure. We have to talk more.
Yes,
would you mind going back to the cube slice plot, please?
This one?
That one, yeah. So for the guitar, how is the tuning head going at both plus and minus 244 and plus 132?
Sorry, how is the what?
How is the tip of the tuning head of the guitar,
Yeah.
not the body? It shows up in both extreme plus and minus.
Yeah.
So how is it? How's it moving at both speeds?
Oh, so it's basically the near and far sides of the shock, and that's the key way that we actually use these measurements to resolve the 3D geometry of the shock, is that the gas that's moving towards you is on the near side, and the gas that's moving away from you is on the far side.
I see.
Yeah.
And the end of this thing is just after a while the gas is not visible to us, or is it the age of the pulsar?
Yeah, I mean, so you have the broadest velocity structure where the gas is actively being shocked, and so as you move farther and farther down the nebula, you basically, have gas that's not being actively shocked, and so it's starting to narrow in velocity structure.
But you can tell the age probably just from the 3D velocity and the distance.
Yeah.
So your explanation of that is totally plausible, but I wonder if you worry about Zeeman splitting, and there's some strong magnetic fields around, and H alpha can be Zeeman splits, and that would also give you something that looks like going towards you and away from you.
Yeah, so the short answer is, and I haven't thought too hard about Zeeman splitting. In principle, there are ways with high enough resolution spectra, you can see the signatures of the magnetic field. I'm not an expert in that, so I have to look more into it, but I do know that there are methods of trying to disentangle that directly from the H-alpha spectra. The problem is that we just don't have high enough resolution to do that.
Okay.
So maybe in the future we can try to work on it.
Okay, so it's a small effect compared to 100
Yes.
kilometers per second.
Yes.
There was another question from this side. Oh, yes.
Do you have any idea why these three different shocks have different shape? For example, the first one is more like straight, but the last one more like 3. Is the environment or the other factor here?
Yeah, so it's a combination of the geometry of the pulsar wind and the structure of the ISM. So for this shock, and I will say people don't agree on this, so like Roger Romani, who's one of the other, like, I would say world experts on neutron star bow shocks, he and I disagree on this. But I think that the structure of this bottom one is primarily due to changes in the ISM density. So basically you can explain this kind of like pinching and broadening just due to the ISM density increasing and decreasing as the pulsar travels through a medium of varying density, and that naturally changes the standoff radius of the shock, which over time will just give you this kind of undulating morphology. But people have also tried to invoke like things in the pulsar wind as being responsible for it. So it's, yeah.
Well, the key is to find an observational way of telling the difference.
Yes.
But you haven't found that. Yes, okay.
Not yet.
Let's thank Stella again.
Is this microphone picking me up? Okay, yeah, I've never used a microphone before, so. Should I begin? Okay, yeah. Hi, so I'm Shaunak. I'm a graduate student at Princeton, and today I'll be telling you about some of my work on characterizing the beautiful fluctuations you're seeing here. Everything I'm talking about is work that's been done with Chris Hamilton, a postdoc at the Institute for Advanced Study, and Eve Alstricker and Scott Tremaine, who are professors at Princeton and the IAS, respectively. Okay, so why study these fluctuations? In case that one beautiful picture wasn't enough for you, here's a lot more. I think right now observations are better than we've ever had them before, thanks to beautiful work from JWST Fang's collaboration, which is shown here. And since I'm here, I am obliged to mention great work from Stella on complementary things on the electron number density, and of course dust mapping in our local Milky Way. Yeah, so those are beautiful observations, but my background is in galaxy dynamics, and my primary interest is really in the consequences of these fluctuations for things like stellar kinematics. So this plot I'm showing on the bottom here is the stellar age-velocity dispersion relation from Gaia data, which roughly shows that the older a star is, the higher its velocity dispersion is of its orbit. And we roughly interpret that as saying stars that are older have had more time to interact with all of these fluctuating features, and so they've been heated up by all these perturbations to of an orbit with a higher velocity dispersion. So just as a sketch calculation of how that might go, for a single star, you can start with its equation of motion, v dot is minus grad phi, formally integrate that to get a delta v over some brief period of time, and then the diffusion coefficient we'd want that governs this type of diffusive heating would be related to the square of that quantity, kind of ensemble averaged. So if you do a Fourier transform and do an average, you'll end up with the diffusion coefficient being proportional to k squared. So that's from the two nablas when you square the delta v, times the power spectrum of the potential fluctuations. So if we want to understand the processes behind these heating things, we need to understand the fluctuations and their density and potential power spectra. So how do we go about doing that? So I've been using these simulations, the Tigris simulations, which are developed by my advisor, Eve Alstricker, and her group. So there's a long, contrived acronym behind that, but suffice to say, it's a kind of state-of-the-art set of simulations about the ISM. to include things such as self-consistent supernova and star formation, as well as ray tracing for the UV radiation field and non-equilibrium chemistry for the cooling. So truly state-of-the-art, resolving things down to parsec scales. And the way they can accomplish that is by being local simulations rather than global ones. So the ones I'll talk about today, there's an R8 simulation, which is kind of the solar neighborhood, so 8 from 8 kiloparsecs, which will be kind of purple throughout this talk. And then there's also this simulation, the LGR4 simulation, which is intended to model conditions closer to the center of the galaxy, so around 4 kiloparsecs in radius. And the surface density there is much higher, so there's kind of burstier star formation and stronger fluctuations. So here's a quick set of snapshots of what the surface density field actually looks like in each of these simulation boxes after you account for all the microphysics. You can see we're dealing with this kind of turbulent, messy, filamentary density field. And we want to ask, how do we characterize that? So the simplest question you can answer, maybe, is what types of values of surface density are present in each of these boxes? So to do that, we could use a one-point statistic, like measuring the probability density function of the surface density fluctuations. And if you do that, you'll find that they're well approximated as log normal. So this horizontal axis is the kind of logarithmic density contrast. And that's something you might expect from theories of supersonic turbulence. But I'll point out that a realistic ISM has some key differences from supersonic turbulence. On the left side, on the R8 simulation, you can see that there are these low-density regions, and those are voids from expanding bubbles that occur due to the energy and momentum feedback that's injected. And on the other simulation, you can also see that when you have those bubbles kind of intersect with each other, you can get regions of especially high density. And you can actually catch some of them right before they collapse into our star or sync particles. So now that you have a one-point kind of statistic, the next step naturally is a two-point statistic. So you can calculate the power spectra of the fluctuations that you see in these simulations. So the left panel here is showing the power of the linear density contrast. And that's kind of important for the potential fluctuations that I've talked about before. The right panel is showing the power spectrum of the logarithmic density contrast. And that's important because we just saw that the logarithmic density contrast is well approximated as Gaussian. So maybe we can use this to build up kind of a model of what the field looks like. The key things you should notice are that both of them are well fit by power laws with slightly different slopes. And what that implies is that all the power in the ISM fluctuations is at the largest scales. So 100, 200 parsec scales. And that's very different than a kind of intuitive picture that I had, at least when I started this, and maybe some of you still have, which is if the ISM is kind of these clumpy cloud structures. So if that were the case, you'd expect to see a bump in the power spectrum at perhaps some kind of characteristic cloud radius. But we don't see that, so that's kind of an interesting aspect of it. The other thing I'll say is that these two simulations are at relatively different environments. So like I was saying, the orange simulation has like a 5 times higher surface density than the purple one, and much burstier feedback, and yet the density fluctuations kind of are on this same spectrum. So I'll leave it to the experts on turbulence theory to understand why that is, but I'll just say for now that that's what we observe in the simulations. Okay, so you might be thinking, we've measured the power spectrum, and I've showed you that the PDF is Gaussian. So is this a Gaussian random field? That'd be great. We can use all our cosmology knowledge. Unfortunately, the answer is not really. So the left panel here is a snapshot of a simulation. And the right panel here is if I produce a log normal random field with that power spectrum that I just measured. Qualitatively, you can see that the rough ratio of bright and dark patches in the surface density is kind of similar. But at a closer glance, like if you look at these blue boxes I've zoomed in on, you can see that the real simulation has all this filamentary structure, which is just not present in a random field. And what that means is that there's spatial phase correlation going on. So in cosmology, we like to do the random phase approximation. That's not going to work here. So you could kind of characterize this further by measuring, let's say, like a bispectrum or a 3-point correlator. But that's a little bit too in the weeds, so I'm just going to leave it at this and say that while it has these nice properties, it's not perfect. Okay, so I spent some time talking about the surface density. Next, I want to talk about the potential, because after all, that's what's dynamically relevant. So the key kind of step towards getting there from what I've just said is to look at the 3D density, so rho instead of sigma. And what you can notice is that the density field is almost separable into this planar portion, which is the surface density, and some kind of vertical structure function, zeta. So this plot over here is a plot of zeta as a function of z. And you can see that kind of these 1 sigma shaded regions around the actual values are not super large compared to the scatter around the mean, So that suggests that this separability is kind of a good approximation, and it's kind of promising because it allows us to connect these two aspects. So another thing you can see is that, once again, strangely enough, the purple and orange curves are on top of each other, despite being such drastically different conditions. So this may be a sign that there is this kind of universal vertical structure present when you properly incorporate feedback and self-gravity and things like that into the ISM. So we fit some complicated hyperbolic secant and exponential to this, and the fits work out well. They're the dashed curves that you can barely see behind the solid ones. But yeah, again, that's all in the details. So finally, just to connect this to the potential, the fact that it's separable means that there's this nice connection between the potential fluctuations and the surface density. So if you start off with the Poisson equation, like this, where I've put in kind of that sigma zeta decomposition for the density field, you can immediately get the potential power spectrum as a function of the in-plane wave number and how far are you above and below the disk. And it looks something like this. So there's a kind of form factor in front that you might recognize from like a razor-thin disk perturbation theory. Then there's the surface density power spectrum, which I told you is just a power law. And finally, there's something that depends on exactly the choice of the vertical structure. But that's just a function of z and k that makes some minor modifications. So now that we have this kind of characterization of the surface density, the potential kind of falls out of it thanks to this decomposition. So here's just a quick illustration of that. The leftmost panel is one of the surface density snapshots from the simulation. And the middle one is the actual potential that the simulation has. On the right side here is what you would reconstruct from the potential as a potential if you were to do that decomposition of the density field as surface density times a vertical structure. And you can see that qualitatively it looks basically the same. So that is to say that this decomposition is good, and this type of analysis of the potential power spectrum should work. So there's a quick summary of everything I just said. Basically, the fields are nice, and here's a quick way to characterize them. But what I want to emphasize as I end is just that really what I've shown here is a toolkit that helps you incorporate the interstellar medium into any kind of dynamical problem that you're interested in. So I'm personally working on applying this to the secular evolution of galactic disks, so disk heating and migration processes. But there's all sorts of other stuff that you can apply this to that I'm always happy to talk about. And if you have any other ideas where you'd like to see what the ISM does to your otherwise pure dynamical problem, I'm always happy to chat about it. Thank you.
So Shaunak, obviously there is also tidal influence from satellite galaxies going through and nearby globular clusters coming through. How significant do you think they are in mixing up and affecting this?
Yeah, that's a great question. So I would say the galaxy is full of perturbers. There's ISM, globular clusters, dwarfs, spiral arms and bars, all sorts of stuff. And what we'd like to do is use our kinematic data from Gaia to understand the contributions of each piece. So I like to think of the ISM as somewhat like a noise floor. Like the ISM will erase stuff due to whatever diffusion it contributes to this power spectrum. So if you want to understand things like dark matter substructure or the contribution of spiral arms, first, this is almost like a contaminant to using kinematics to understand things like that. So that's something that I'm also working on is how you can effectively use Gaia data to constrain other things once you factor in the fact that this ISM is ubiquitous.
Okay, we'll start from there. Go ahead.
So I guess related to what I asked in the second part, did you get a chance to look at whether what you measure from this fluctuations, if it's enough, like scattering of GMCs, if it's enough to expand thick disk or something else?
Yeah, so I didn't have time to go into the details here. I'm happy to talk about it afterward as well. What we find is that the ISM contributes greatly to the heating, so it can't account for all of it. The way I've done this is basically I have the simulation box, and I can integrate test particle orbits to literally feel the fluctuations that are in the simulation. So when you do things like that, you will produce heating and stuff that accounts for maybe half the total observed heating. But of course, these simulations don't have the spiral arms, the bar, the dwarf galaxies, so I think it's a reasonable fraction. One thing I'll say is you mentioned kind of GMC scattering, and a consequence that we found is that although that's a very intuitive picture, it's a very inaccurate picture. So the turbulent kind of fractal almost nature of the ISM fluctuations leads to very qualitatively different scattering behavior than, for example, spherical point particle clouds. So Yeah, so Eve has always joked we should ban the word GMC from my thesis, but yeah.
Tony?
Well, but GMCs do exist.
Yes.
I mean, they are observed, and it's not surprising that the fluctuation energy comes from larger sizes, because that's what creates the GMCs. Their
Yes.
lifetime is not that long; it's only 30 million years, and so you have to constantly be making new ones, and the energy flows through that scale. But there are definitely GMCs as a thing. I mean, if you observe in molecular lines, the galaxy is in fact full of clouds.
Yeah, so, okay, maybe that was a strong statement I said. I could amend it to say that GMCs are responsible for a qualitatively different type of scattering than the rest. And we think that the rest is contributing more to the observations, like the observed velocity dispersions, than the GMCs.
And of course, at Princeton, the effect for GSC should be called the Spitzer-Schwarzschild effect.
Spitzer-Schwarzschild diffusion, yeah. So Spitzer-Schwarzschild diffusion is what I was alluding to. And what we find is that a realistic ISM produces totally different diffusion than Spitzer-Schwarzschild.
I'm not alive to be upset about it.
Yeah.
Elisa?
Hi, that was very interesting. I have kind of a nitpicky question, but I'm curious. Can you go back to the PDFs that you showed of the two different simulations?
Yes.
So you said that the one on the left has voids from expanding bubbles.
Yes.
It doesn't have the intersecting shells, etc. And the one on the right does. But in the real galaxy, both things are present at both places. And so I'm curious why these are still realistic.
Yeah, so I would say that the simulations also have somewhat different resolutions and different things that go into basically the measurements that you can make. So the LGR4 box, okay, I tried to hint at it with the sizes of those little squares that are now invisible, but the LGR4 box itself is smaller, but the number of grid cells is the same, so it goes down to smaller scales where you expect overdensities to be more visible. So I think the resolution of this orange simulation is down to 2 parsec scales, but the purple one is limited to 4 parsecs, so you expect these about to collapse overdensities to be at the kind of smallest grid cells. So actually, if you smooth this simulation, like look at what is the variance as a function of scale, then these two kind of match up if you put them on the same footing. Yeah, as to why the voids aren't present in LGR4, I think that's just because there's overall a higher surface density. So the means are also different with these distributions. So yeah.
Okay, we have to. Oh, one last question, Eric. Go ahead.
How many phases are in this interstellar medium?
Yeah, so you've called it the 3-phase ISM. I think as of now, we've incorporated a lot of different phases that you can characterize in different ways. So that's not really my work, but I can point you towards some other papers that characterize the kind of velocity PDFs and temperatures in different phases. I think they break it up into 4 or 5 different things based on if it's neutral or molecular and its temperature and where in the galaxy is it. So they actually find fountain flows in trained clouds and things like that.
We don't need to keep it a small number because we have AI.
Yeah, true, yeah.
Okay, let's thank Shaunak again.
Okay, so hope this is working. And wait a minute, you can't see anything. Okay, so I'm happy to be back. It's so much fun. The snowstorms are missing. Usually when I come, it's kind of full of snow, but otherwise it's great. And I would like to just talk about a paradigm, actually, 3 paradigms which are all interconnected. There's the standard idea that when you go to high redshift galaxies, they have a large gas fraction. So the gas over the total baryonic mass is order 50%. they have baryonic-dominated rotation curves. That means if you measure the dynamical mass, V rod squared times the effective radius of an exponential disk divided by g, then it's equal to m gas plus m star, and that they have large random component of their kinematics. That means V rod over sigma is of order 4, and compared to present-day galaxies where it's even larger than 10. And all of these three paradigms are actually interconnected by an analysis of the stability of disks. If you take disks, then the stability parameter is the tumor Q parameter, which has a stabilizing component, which is the velocity dispersion of the pressure, and the shear, which is the epicyclic frequency, V rod over R, and the destabilizing component, which is gravity, G times the surface density. And the standard wisdom is that Q has to go below 1 in order for the disk to become gravitationally unstable, and then it self-regulates to the edge of stability, which is of order Q equal to 1. Now, you can rewrite this in a different way. Q is square root of 2, dynamical mass over gas mass, sigma over V rod. And you see immediately if the gas or the baryons in these high redshift disks dominate and are similar to dynamical mass, then sigma over V rod has to be of order unity and can't be that much smaller. It just follows from this kind of thing. So everything seems to be fine, and we think we know everything. But of course, the universe is much cleverer than we, and so it turns out it doesn't fit. And this is one example, Rebels 25, which I stumbled on. There are some carbon-1, there are 2 emission observations about the kinematics, and then a little bit about the stellar component. It's a redshift 7 galaxy. The effective scale length, it's an exponential disk with surging is of order 1. So the exponential RE, the sigma goes as e to the minus r over e, is of order 2 kiloparsecs. You think this is reasonable. And the rotation is quite large, 370 kilometers a second. The stellar mass is tiny. 6 to the 9, this is nothing. It cannot really explain 370 kilometers a second. But the star formation rate is big, 200 solar masses per year. And so the idea was it's all gas. And then what the people basically do is they determine the dynamical mass, V rod squared times R over G. And they get something like 10 to 11, and they say this is all gas. And so the gas mass is then the dynamical mass minus the stellar mass. It's of order like this. And the gas fraction is of order 1. So it's a gas-rich galaxy. Everything is as you would expect for these high redshift galaxies. But then they discovered, for just looking at the emission at the broadness of the spectrum, that the velocity dispersion is only 30. So V rod over sigma is 11, like the Milky Way. So it's an ultra-thin, very quiescent disk forming stars like crazy and should be strongly gravitationally unstable. Okay. So the question is this a puzzle? And they say it's a big puzzle. I just wonder what happens here. This doesn't look, I redo it again. This is how I look usually. You know what I mean. This is what we are as astronomers, okay? Good, I hope it stays like this, I'm not sure. So this is, so let me now do it graphically because that makes it more clear. What you see here is the rotation velocity as function of distance of observed in this kind of galaxy. And if you believe it's all due to the disk mass, then you basically can fit an exponential disk to it. And then you get this kind of red curve, which fits the data very well. The disk mass you need is 2 10 to 11 solar mass, the effective radius you know. And then you can work out what kind of dispersion you would expect if you have a tumor Q of order unity, which is what we all believe. And then you can go down in Q, and these are the observations. And what you find is, basically, let's say we focus on the effective radius, that if you take a reasonable Q of order 1, then the rod over sigma should be 2 or 3. This is exactly what we would expect for the high redshift galaxies. But what we see is down there. So V rod over sigma actually out there is of order 20. So something is not really working. And the question is, what is wrong? And what is wrong is, well, you could simply say, okay, maybe this disk has a small q. Why not? How can you enforce it on the disk that it has to be 1? But you can immediately show that a disk would become gravitationally unstable. Here you see an example. And this instability leads to lots of clumps. And these clumps generate motion that is not radial, not rotationally. And for an observer cannot really distinguish between collapse or any other irregular motion. The observer just sees the broad line width, and that leads to large sigma. It's not a pressure. It's the opposite of a pressure. It's collapse, but who cares? The sigma would be seen, and the tumor Q you can show immediately turns up to be 1 on a short time scale. And that is not what we see. We see 0.1. But the disk should generate a kind of a tumor Q due to the random motion, which is that large. You might say maybe it takes too much time, too long time. The disk is maybe too young. But the time scale in which you reach this Q is given by the tumor time scale. It's 0.1, the orbital time, and then there's a factor Q in it. And if Q is of order 0.1, it's 1% of the orbital time, which is a few 10 to 6 years. And the disk would have had time to do this. So the question is, what is wrong? I know, you're a clever guy. I know this. That's why I'm always here, and of course you got it right. But you have to show it, actually. Actually, absolutely right. You know, your paradigms that dark matter is unimportant, you should never take as granted. You just test it. And that's what I did in this kind of plot. So what I did is I simply added a dark matter halo to what the people forgot. For I don't know why, but they forgot about dark halo because. And so what I did is I took a standard NFW halo. If I know the Wheel mass, I know the Wheel radius at redshift 7. And then I know the density distribution. And then I can fit the rotation curve which the dark matter would generate. Then I have to add a disk. And I do the most conservative part. I take a cosmic baryon fraction, the biggest disk I can put in, 16%. I know the effective radius of the exponential disk. I get another rotation velocity for that. And then I add it all up. And then I have the only free parameter is now the Wheel mass of the dark halo, because everything else is given. And I now choose the Wheel mass so that I can fit the observations. And that's basically what you get. You know, the red is now the fit. And you see the blue part is the dark halo. And this part is the disk. There's no other way. If you want the disk to crunch up, you need to go beyond cosmic baryon fraction. And you see that this galaxy, despite standard ideas, is completely dark matter dominated. And when you now look at the predicted Q=1 dispersion between 0.5 and 1, it works perfectly with the observations. The reason is that this wants to become gravitationally unstable, but the dark matter stabilizes it. So it has to change its scale height. The scale height has to be very small so that it becomes dense enough to become gravitationally unstable. It must be ultra thin for that, but it can only be ultra thin if the dispersion is small. And that's why it basically does exactly like that. Now you might ask, why do other galaxies not do the same? Why are they not dark matter dominated so much? And okay, this can also be explained very simple. It depends on specific angular momentum. The size of a disk is given by the specific angular momentum of the material inside the disk. We usually normalize the specific angular momentum J disk by RV times VV. RV is the Wheel radius of the halo. VV is the circular velocity at the Wheel radius given by that. It's called the lambda parameter. And the distribution of lambda parameters we know very well. For disks is like this. So it peaks at 0.035, which is 1 over the collapse factor of this kind of thing. And now I can use my two-component model and predict what effective radius I need in order to have a certain amount of lambda. You know, most of them are sitting here, and you see the effective radius is much smaller than 1. But Rebus 25 has an effective radius of 2. So you see its lambda is actually quite large. It's an unusually large specific angular momentum. And now if you use this lambda again and now plot V rho over sigma, just using my simple trivial model, that's the only thing I can do, you know, simple analytical back on the envelope simulations, then you see how V rho over sigma depends on lambda. And you see indeed it's very, very small when you are kind of compact, because then the disk is self-gravitating, but it quickly increases when you go beyond this peak. And as we know the lambda for Rebus 25, we know where it should sit, and it sits exactly where it should be. So there is no mystery. You do not have to do any numerical simulation to understand it. You just sit down with a glass of coffee, some beer in Bavaria, and do a back on the envelope calculation and you get it. And my conclusion is don't rely on paradigms. So thank you very much.
Thank you, Andy. We agree with your conclusion. The question is, there used to be a model of dark matter that was suggested by a guy named Burkert, where there is a core and the dark matter doesn't have a cusp, right? You know this guy that suggested that. Did you use that model or did you use the NFW?
No, I used NFW.
Well, so is it evidence against your model?
Oh, no, I don't think so. I still have the freedom to fill the central region by bulge. You know, the problem is this declining part here is not really very well resolved. So this is, it could be a kind of resolution problems, and actually the velocity could remain constant like this. And the people believe that the increase in the dispersion you see is due to an additional bulge component, which is not resolved. So in this region, I could put a core of a dark matter halo in because it's compensated by a possible stellar bulge component. And cores are generally not that big. But I don't need it. And I tell you, I don't really care. You know, whether dark matter halos have a core or no core, that's the universe decides on that and not me.
To see if it's evidence against core, but you're saying that...
No, it's not. Because actually this part I would exclude. I would just go to this part, and there the cores are unimportant.
Okay, thank you.
Yeah, but thank you for mentioning it.
You attempt to say the puzzle. Are these dark matter halos of 10 to the 12 at redshift 7 common enough to make this normal galaxy?
I don't think so. Actually, I don't think. I don't even know. Maybe they should exist. They might not be very common, but you do not really know how many of these galaxies exist.
Right.
Then you find the peak of the lighthouses, and you need to do a statistical analysis. But it's a very good question. Where would you see them? In which cosmic environment would you expect them? I would think in a cluster environment or a kind of big cluster environment. And how often? That's a very good question.
Yeah, it's a good question also because you find a large spin parameter, so
Yes.
this should be a subset of the entire population of such objects.
Absolutely right. So that would be an interesting test of. This is just an idea. It might still something else might still be important.
Okay, over there.
So thank you. I like your talk. I like your interpretation. But I also know that the people who discovered this disk also have reason to believe the gas mass indeed dominated the dynamical mass, because you can measure the gas mass from the dust mass. You know there should be a conversion factor of 100, and you have this global Schmidt law that can convert spatial results, not picture, really to spatial result, gas mass density, and do integrations. So do you think? What's your comment on that?
Yeah. Well, I thought, of course, about this. It's a very good question. My answer is I don't think the gas mass can be that high. And the reason is very simple. If you take the carbon-2 emission and from that work out the conversion factor of carbon-2 luminosity to the gas mass, which you get, then you need a factor 60. You measure the luminosity and need to multiply with 60, and then you get the gas mass which the people believe must exist to explain the dynamical mass. And the factor 60 is just simply too high. It's never ever observed. It's more like the factor 10, 20. And this is exactly the factor I get when I reduce the disk mass to that value and compensate what the dynamic mass is by the dark matter halo. So already this conversion factor from carbon to the gas mass tells me the gas mass can't be that big. And it fits perfectly. If I do my disk, get the gas mass from my disks, I get a wonderful, perfect. So that's an independent check of exactly this question.
Okay, thank you.
There is another reason why it couldn't be so large, the gas mass, because it means that you're observing it at a very special time. Because with a star formation rate of 200 solar masses per year, you could have seen it for a Hubble time, and then it would have been a much larger stellar mass.
So then several reasons. So I think dark halos are important.
Tony?
So one thing about this kind of object is that the way they're selected, you almost always find a bunch of other ones relatively nearby. And I don't know whether that's the way they really are, or that you don't actually find them unless there are a bunch of things that are together in a proto-cluster. And giving you enough brightness in the far infrared to actually detect them. But but if you have one of these 10 to the 10 solar mass things, there's almost always another couple 10 to the 10 mass things within several times the diameter of the first one, and at the same redshift.
Yeah, that might well be. Close by is the closest object that fits this galaxy is the Milky Way.
Mm-hmm.
Because it has a small dispersion, it has a large rotation. Indeed, in this Rebus 25, I heard they observe spiral arms, which is very unlikely, maybe in the redshift 7, but there, because it's so kinematically cold, it makes a lot of sense. Yeah, the only difference is the Milky Way has 10% gas, and this still has a large fraction of gas. Even if you reduce it now by the dark matter halo, it's more than this at 8 to the 9 solar masses of stars, which we have. So it's I'm not sure there is a counterpart close by in this, but maybe there are. Yeah.
Well, thank you, Andy, for explaining something that looked puzzling to observers, and that's what theory is for. Thank you.
Yeah.
Okay, so hi everyone. My name is Will Golay. I'm a second-year grad student here, and I'm going to be talking to you today about a tidal disruption event that turned out to be pretty interesting and special. This will be the first example of a non-relativistic outflow from a TDE that's ever been observed. We have many examples of relativistic outflows launched by supermassive black holes that have been resolved, as we all know, but this is one of the very first examples of a non-relativistic outflow from a supermassive black hole in general, but specifically one triggered by a TDE as well. So just as a reminder, what are TDEs? TDEs are when a star is disrupted by a supermassive black hole in the center of a galaxy. These were first theorized in the 70s and 80s and were shortly discovered thereafter, first off in the X-ray. And these are interesting because we have a new rapid amount of accretion onto a black hole that was previously not doing anything. And so we have an opportunity to probe these very first days of accretion, days and months of accretion onto an object that previously had, that was previously quiescent. So what are the conditions for a supermassive black hole to cause a tidal disruption event? The most important one is indeed that the Roche radius of the star and the supermassive black hole, which in the rigid body approximation is given by this equation here, has to be outside of the innermost stable circular orbit. Otherwise, the star will be swallowed whole, and you will never actually see a disruption. But let's say the other case happens. So for about a solar mass star, it turns out that a 10 to the 9 solar mass supermassive black hole is the upper limit for what you can have. If you have a supermassive black hole less than that and you have a star of order a solar mass, turns out what will happen is about half of that material will be accreted and the other half will be ejected. And this is really important for understanding how supermassive black holes play a role in the central environment of their galaxy, but also more broadly. It's been thought that TDEs might be the first example of material that gets launched and ejected into the circumnuclear medium. And these very early stages of understanding how this material is launched will be really important for understanding these broader the broader structures that we see surrounding relativistic material launched by supermassive black holes. So there are a lot of different pictures for what TDEs could look like. This is just one of them, and I wanted to show this one in particular because it highlights the origins of where we think the observables come from in TDEs. So if we have a picture like this one, where we can unify the TDE picture in a very similar way to the way we do with AGN, where probably all the, you could argue that all these sources come from the same underlying population of tidal disruption events, and really the only difference that we're seeing are ones that have to do with one or two parameters, such as in AGN, the viewing angle. And what's nice about this particular picture here is we can see that the X-ray, optical, and typically the IR, which is what you see as reprocessed optical, that all traces the accretion process onto the black hole itself. But you could also have a picture where TDEs discovered, say, in the X-ray versus TDEs discovered in the optical, which is what currently dominates the population from surveys like ZTF, could actually be from two distinct different kinds of objects or TDE situations. And so that's the goal we're trying to understand with these TDEs now is, okay, what are the properties of TDEs as we discover them across the spectrum? You know, we have these X-ray TDEs, which show variability for very long periods of time. And we have these optical TDEs, which is this very big population of sources that we feel like we understand pretty well. But what's nice about this picture here is that in nearly any of these scenarios that you can come up for what are the origins of TDEs, the radio is the only one that traces outflows, is the only one that's tracing material that gets launched away from the black hole after the disruption. And this is the unique angle that radio observations provide for understanding TDEs, is that they trace the outflows that are launched. So, okay, what do we know about radio emission from TDEs? So far, all of the known radio-detected TDEs have been in the optical, except for a very few cases. We have our, here on the right, I'm showing radioluminosity on the y-axis versus days from the initial optical detection. And up at the top, we have these really bright sources, which are our classic on-axis jetted cases. And then we have this big group of other sources that are all much lower luminosity and also are turning on up to 1,000 days, so 2 or 3 years after the original optical discovery. So this is one of the unusual discoveries that was made by Yvette Sendes, who was a postdoc here in my group. And what's interesting is that you only see prompt radio emission in 20% of the cases, but you're twice as likely to see delayed radio emission, 40%. And recall that these are all only optically discovered TDEs, except for, of course, our on-axis jetted one, which was discovered in the gamma rays. And we have this significant diversity in energy, and again, this divide between these two different cases. So, okay, if there are on-axis jetted TDEs, where are the off-axis jetted TDEs? Well, you might guess that all of these down here are off-axis jetted TDEs, but it turns out that these luminosities are too low, and also if we look at the evolution of the radio spectrum over time, we can do what's called an equipartition analysis, which I'll show a little bit of for my source that I'm going to be discussing. And what you end up with is that most of these sources, what you can infer is that the launch of the radio emitting material occurred after the optical flare, which means that there was a delayed launch. And this seems to be a very prevalent among this lower population. But there are some suspected examples of off-axis TDEs, which I'm happy to discuss offline. Okay, so what do I want to show here today? So we have here one of these TDEs that is an infrared-only TDE. So this was a unique one that was discovered about a year ago, and it only has detections in the mid-IR. Here's the WISE light curves up at the top, and here I'm showing the radio light curves of this source. And here's the name, WTP14ADEQK. It's just a beautiful, beautiful name, which I did not come up with. And this was a great source because of many different properties, but I think the most important one to point out here is that this thing is nearby. And this is what allowed us to access the sufficient resolution with the very long baseline array to actually resolve this source. So I want to briefly highlight that this source's host galaxy is relatively nearby, and we do understand it quite well. There is some pre-existing radio emission, but we're able to explain that due to star formation in this galaxy. So we were able to take an optical spectrum and verify with classic BPT diagrams over here to classify this as a star-forming galaxy, and we're able to indeed confirm that radio emission that existed prior to the transient was indeed from star formation and not from a hidden AGN, for example. So, okay, so what can we do with our spectrum? So we took a VLA spectrum of this thing. We got the full VLA band, 1 to 50 gigahertz, which was great. And what we can do is we fit for a peak frequency, a peak flux, and then we also fit for a cooling break, which I'll discuss briefly. As you can see, there's something weird going on here. And what we have is we have an equipartition model, which allows us to map these parameters of really the luminosity and the peak frequency to parameters that have to do with the density and the magnetic field and the size and the energy. So those are our 4 numbers that we get out of this. We get a radius, an energy, a magnetic field, and a number density. And what we find is when we get this radius, we get some number here, and then we know when this radius was measured. It was measured about 10 years after the observation, and if we just take that radius and we divide by roughly 10 years, we end up with a velocity of about 0.03 times the speed of light, which is indeed non-relativistic. Let's say we delay this thing by 1,000 days because we don't have an initial non-detection in the radio. It turns out, again, that velocity is still only 5% the speed of light, so indeed non-relativistic. So we went through all this effort to fit a spectrum and plug in these numbers into these crazy equations, but why don't we just, to get the size, I'll come back to the cooling break, why don't we just take a picture of the thing to get the size? So that's what we did with the VLBA. So here what I'm showing is the VLBA image that we were able to get for this source. Those are the contours. There's the position inside of the galaxy, the red dot there. So indeed it is at the center where we would expect our supermassive black hole to be. And okay, you might argue this isn't particularly interesting looking source. It just kind of looks like a blob. But it turns out when you fit this thing with a 1-component, just simple resolved Gaussian, we're able to get a size of about 0.1 parsecs. Which corresponds almost exactly with the size that we inferred from the spectral energy distribution fitting that we did earlier. So we were able to show with 2 independent methods, both with the VLA and with directly resolving the source with the VLBA, that indeed the size is about only 0.1 parsecs 10 years after the optical flare. So what does that tell us? One quick thing, and then I'll end here. I'll end on this slide here. One quick thing is that what does this tell us? That indeed, if this were a off-axis jet and not a non-relativistic outflow, what we would see is that the delay, the 2-year delay, would indeed have been caused by the deceleration of the off-axis jet, but the VLBA image would have been much larger in that case because it would have had much more time to travel in the plane of the sky. But we were able to show that indeed the size of that source is quite small, and so the only explanation for the source to be that small 10 years after the fact is a non-relativistic outflow that was launched no earlier than whenever the TDE happened, but it could have been launched after the fact, and we have upcoming data that will allow us to constrain whether or not this source had a delayed launch like many of these other ones, or if it was launched at the exact same time as the infrared flare, which would be abnormal compared to the optical TDEs. And that's pretty much it. Thank you.
Will, there is an interesting coincidence. If we take your beta, the velocity divided by the speed of light, square that, multiply by a solar mass times 1/2, we get the kinetic energy of the ejecta, and that amounts to 1051 ergs, which is pretty much what you often get in explosions.
Yeah, so in our case we got 10 to the 50, yep.
10 to 50, well, does that include the radiative efficiency? Oh,
this is just from the this is just from the radio spectrum.
Okay, so that's the kinetic energy.
Yeah.
Then the 50. Yeah, that's very reasonable.
And that just comes out of the equipartition.
Okay.
Yeah.
Yes.
What fraction of radio loud TDEs are nearby, bright enough to resolve and detect with VLBA? Is this a really rare thing? Like in the future, when we have tens of thousands of radio TDEs, is it hopeless to?
Yeah, so that's funny that you mentioned that, because this is something I've kind of bounced around in my head as a fun little number to calculate and actually put out there, because indeed, these are this particular source was at 0.018 redshift, and most of we're quite limited with the VLA to essentially TDEs less than 0.1, and that's with the VLA sensitivity. The VLBA is far less sensitive, just by number of dishes, and so we're even more limited. I would say there's the main constraining factor is how bright they are, and there's been very few that are quite this bright. There's probably of order 5 or 6 currently out of maybe 100 discoveries. So 5% out of out of all the TDEs, if we're discovering tens of thousands, that could get overwhelming. Yeah, so we'll have to pick and choose.
Okay, we reached our time limit, so let's thank Will again.